AP Chemistry Unit 4 is a fundamental unit in the course. It covers chemical reactions and it lays the foundation for a big part of the rest of the course. Hi there, my name is Jeremy Krug, and this is the place for all things AP Chemistry. You're about to see the 10 most important things you've got to know from Unit 4. If you're new here, welcome. Take a look around, check out my AP Chemistry playlists, that's where the action is, and make sure you subscribe. YouTube tells me that over 80% of you haven't subscribed yet, so what are you waiting for? It's free and it's an easy way to help out the channel. And if you're serious about getting that 5 on the AP exam, check out my ultimate review packet for AP Chemistry. It's got the full review videos for every unit, complete study guides, practice questions, and 2 full practice exams in the AP Exam Simulator. You can get a free sample today over at ultimatereviewpacket.com. Now, here are the 10 things you've got to know from Unit 4. Number 1. Chemical reactions are usually signaled by a large change in temperature, the formation of a precipitate, or a color change. Physical changes are usually signaled by a change in form or state. Chemical reactions include processes like burning, rusting, growing, or digesting. And when a chemical reaction takes place, we'll observe a change in odor, a change in texture, formation of a precipitate, or a large change in temperature. Physical changes, on the other hand, are changes in the appearance, form, or state of matter of a material. This might include tearing, melting, condensing, or dissolving. Sometimes a change might even have characteristics of both the physical and chemical change. For example, imagine an ionic compound dissolving into water. The solid becomes an aqueous solution, and there's no fundamental change in the identity of the substances present in the mixture. So we could say this is a physical change. But we could also say that this same ionic solid is dissociating into separate ions. And when this happens, ionic bonds are breaking due to the strength of the ion dipole forces in the mixture. So it also has characteristics of a chemical reaction. It's the same process, but a case could be made that it's both a physical change and a chemical reaction. Number 2. Chemical equations must be balanced. Both the reactant and product side of a reaction must have equal numbers of atoms for each element. For example, in this chemical equation, we notice there are 2 oxygen atoms on the left side, but only 1 oxygen on the right side. So we balance that by placing a 2 in front of the Na2O on the product side. We see there's only 1 sodium atom on the left, but 4 sodium atoms on the right. So we place a 4 in front of the Na on the left to balance the equation. What about this equation? We see there are 4 phosphorus atoms on the left and only 1 phosphorus atom on the right. So we place a 4 in front of H3PO4 to balance the phosphorus atoms. Next, we can balance the hydrogen atoms by seeing that there are 2 hydrogens on the left, and on the right we have 4 times 3, which is 12 hydrogens. So to balance those, we place a 6 in front of water to have 12 hydrogens on both sides. Notice that the oxygen atoms are now balanced because we have 10 plus 6, or 16 oxygen atoms on the left, and on the right we have 4 times 4, 16 oxygen atoms also on the right. How about this equation? In this combustion equation, we have 5 carbon atoms on the reactant side and only 1 carbon atom on the product side. So we place a 5 in front of carbon dioxide. Then we see that we have 12 hydrogens on the left, only 2 hydrogen atoms on the right. So we can multiply the water molecule by 6 to have 12 H's on both sides. Next, we see we have 2 oxygens on the left, but we have 10 plus 6, or 16 oxygen atoms on the right. So to balance 2 versus 16, we need to multiply the O2 on the left by 8. So make sure you can balance equations. Number 3. Net ionic equations reflect an actual chemical reaction taking place, in which only the reacting species are listed, and the spectator ions are not included. Imagine a reaction where a few drops of acetic acid are added to a beaker containing a solution of sodium carbonate. We can start by writing out the reacting substances. Acetic acid has the formula HC2H3O2, and sodium carbonate is Na2CO3. The ions will swap, so the products are sodium acetate and carbonic acid, H2CO3. And of course, balance the equation. Then we can write substances in the form of ions when they exist as ions. Acetic acid is a weak acid, so it retains its original formula. Sodium carbonate is a soluble ionic compound, so we write it dissociated into ions, sodium ions and carbonate ions. On the product side, sodium acetate is also a soluble ionic compound, so it's written in its dissociated ion form as well, sodium ions and acetate ions. Carbonic acid is a weak acid, so it's not dissociated. Once again, we maintain our balanced equation. One other detail we should remember is that carbonic acid at normal atmospheric pressures does not really exist. It undergoes what's called a gas evolution reaction, in which H2CO3 actually decomposes into water and carbon dioxide. Notice that sodium ions are found on both the reactant and product side of the reaction. The sodium ions are completely unchanged, so we say sodium is a spectator ion. That just means it doesn't react, and we don't include it in the net ionic equation. Remember, net ionic equations include only substances that actually participate in the reaction. Number 4. When writing a net ionic equation for a precipitation reaction on the AP exam, any product containing sodium, potassium, ammonium, or nitrate ions will be soluble, and its components will be spectator ions. The other product will be the precipitate. So imagine a test tube containing a 0.1 molar solution of silver nitrate poured into a beaker containing a solution of dilute iron 2 bromide. Well, we know ionic compounds in solution actually exist in ion form. So AgNO3 is written as silver ions and nitrate ions. Iron 2 bromide is also in solution, so it also exists in its ion form, iron 2 plus and bromide ions. The ions try to switch partners. On the AP exam, one and only one of these pairs will form a precipitate. The pair containing nitrate, potassium, sodium, or ammonium ions will be spectator ions. In this case, the silver ions and the bromide ions combine to form AgBr. That means that Fe2 plus ions and nitrate ions are the spectator ions. So the overall net ionic equation is Ag plus Br minus yields AgBr. Number 5. When solving reaction stoichiometry problems, use the 3-step process. Step 1, convert to moles. Step 2, mole ratio. And step 3, convert to final unit. In this problem, we have a balanced equation, and a chemist pours 2.52 grams of water into a beaker containing 7.44 grams of powdered sodium oxide. And this reaction takes place to completion. What mass of sodium hydroxide is produced in the reaction? In this problem, we start with both quantities of reactants, 2.52 grams of water reacting with 7.44 grams of sodium oxide. And the goal is to determine how many grams of sodium hydroxide are produced. We'll do both conversions. Step 1 is to convert to moles. So grams go on the bottom and 1 mole goes on top. We consult the periodic table and see that 1 mole of water has a mass of 18.02 grams. Grams cancel top and bottom. Step 2 is the mole ratio, where we use substances from the balanced equation in our conversion. We put water in the denominator so it will cancel, and we're converting to sodium hydroxide. According to the balanced equation, there are 2 sodium hydroxides for every 1 water. Water can cancel top and bottom. We're in moles of sodium hydroxide, but we want to be in grams. So step 3 is convert to final unit, which is grams. Moles need to go on bottom, and grams go on top. We consult the periodic table and see there are 40 grams in 1 mole of sodium hydroxide. Moles cancel, and our answer is 11.2 grams of sodium hydroxide. We need to do the same thing for the other reactant. We put grams on the bottom, 1 mole on top. According to the periodic table, there are 61.98 grams in 1 mole of sodium oxide, and we can cancel grams. Step 2 is the mole ratio. This time, sodium oxide goes on the bottom and sodium hydroxide goes on the top. According to the balanced equation, this is a 2-to-1 ratio. Sodium oxide cancels. Lastly, we convert to our final unit. Moles on bottom, grams on top. There are 40 grams in 1 mole of sodium hydroxide. We cancel moles and we do the math to get an answer of 9.60 grams. When we have two answers like this, we always select the smaller answer. So in this reaction, we actually produce 9.60 grams of sodium hydroxide. This means that sodium oxide is the limiting reactant, since that reactant produced the smaller amount of product. Water, on the other hand, is the excess reactant, so we'll have water left over after the reaction. How about this question? What mass of the excess reactant remains after the reaction? Well, we know that we actually use 7.44 grams of sodium oxide, since that was the limiting reactant. It was used up. We're trying to find how many grams of water we're going to use. So we go through the same three-step process. Step 1 is convert to moles. So grams on bottom, 1 mole on top. And there are 61.98 grams in 1 mole of sodium oxide. Step 2 is the mole ratio. This time, sodium oxide goes on the bottom and water goes on top. According to the balanced equation, it's a 1-to-1 ratio. We cancel sodium oxide, and finally, we convert to moles. 1 mole on the bottom, and there are 18.02 grams in 1 mole of water. So this tells us we're actually going to use 2.16 grams of water. According to the problem, we had 2.52 grams of water available to us. And we just calculated that we used 2.16 grams. So we subtract and find that we'll have 0.36 grams of water left over after the reaction. We can use the same process to solve stoichiometry problems involving solutions. For example, take this balanced equation. A chemist pours 5.0 milliliters of 0.10 molar lead-2 nitrate solution into a beaker containing excess sodium chloride solution, and the reaction proceeds to completion. What mass of lead-2 chloride precipitate is formed? Once again, we start by writing down what we begin with, the 5 milliliters of lead-2 nitrate. In liters, that's 0.0050 liters of lead nitrate. And the question is, what mass or how many grams of lead-2 chloride are formed? Step 1 is convert to moles. So liters go on the bottom and moles go on the top. The problem tells us that the concentration of this solution is 0.10 molar. That means 0.10 moles for every 1 liter. Liters cancel top and bottom. Step 2 is the mole ratio. So lead-2 nitrate on the bottom and lead-2 chloride on the top. The balanced equation tells us this is a 1-to-1 mole ratio. We can cancel lead-2 nitrate top and bottom. We're now in moles of lead-2 chloride, but we want to be in grams of lead-2 chloride. So our third step is to convert to that final unit of grams. Moles go on the bottom, grams go on top, and the periodic table tells us there are 278.1 grams in 1 mole of that substance. Moles cancel, and our calculator tells us we produce 0.14 grams of lead-2 chloride. Number 6. An acid-base reaction involves the transfer of protons, and a proton is just an H+ ion. An H+ donor is an acid, and an H+ acceptor is a base. So in this acid-base reaction, acetic acid is an acid because it's donating H+ ions, or protons, to the base, which is water. In the reverse reaction, hydronium ion acts as an acid and the acetate ion acts as a base. And this is because the hydronium donates a proton, or an H+ ion, to the base. Every acid-base reaction has 2 conjugate acid-base pairs. One of these pairs here is acetic acid and acetate ion. The other one is hydronium and water. Remember, a conjugate acid always has exactly 1 more H+ than its conjugate base. Number 7. Strong acids ionize completely in aqueous solution, and weak acids do not. In AP Chemistry, you're expected to know 6 strong acids, and these are their formulas. As is the case with all acids, strong acids react with water to form hydronium ion and the conjugate base. And this is what those dissociation reactions look like. We call these strong acids because they're completely dissociated in solution. That means that every molecule of those strong acids gets dissociated into ions. Weak acids, on the other hand, don't do that. Only a fraction of their molecules get dissociated into ions. For example, HBrO2 is a weak acid, so when it reacts with water, only a fraction of those acid molecules turn into hydronium and the conjugate base. That's why we use a reversible arrow for weak acids. Number 8. The stronger an acid is, the weaker its conjugate base will be. The stronger an acid is, the stronger the base it reacts with will be. So in this reaction, we have the strong acid HCl reacting with water. Since HCl is a strong acid, its conjugate base, the chloride ion, must be a very weak base. Remember, the stronger the acid, the weaker its conjugate base. And since HCl is a strong acid, that means that water must be acting as a strong base in this reaction, because it's accepting every one of those protons. Since water is a very strong base here, that means its conjugate acid, hydronium, must be acting as a very weak acid in this reaction. What about the reaction of a weak acid like bromous acid? Since it's a weak acid, its conjugate base, the bromite ion, must be a stronger base. Remember, the weaker the acid, the stronger its conjugate base. And since bromous acid is a weak acid, water must be acting as a weak base in this reaction, because it's not accepting very many protons. Hydronium must be a stronger acid in this reaction. Number 9. An oxidation number, or charge, can be assigned to any atom in any compound or ion. It's possible for the same element to have multiple oxidation numbers, or charges, in different situations. For example, take chlorine. Elemental chlorine, like all elements by themselves, will have an oxidation number of 0. The chloride ion, Cl negative, has an oxidation number of -1. When it's in the perchlorate polyatomic ion, we need to do a calculation. Remember, oxygen in most ions and compounds has an oxidation number of -2, and there are 4 of them. Since the whole ion has a total charge of -1, we can use algebra to determine that chlorine has an oxidation number of +7. What about nitrogen trifluoride? Well, when oxidation numbers aren't obvious, the most electronegative atom in the compound can be predicted using the periodic table. So in this case, fluorine has an oxidation number of -1 since it's a halogen. Using algebra, nitrogen can be X, and there are 3 fluorine atoms at -1 apiece, and the compound has a total charge of 0. So nitrogen has an oxidation number of +3. Number 10. Every redox reaction is composed of 2 half reactions. One is an oxidation, where something is losing electrons. The other is a reduction, where something is gaining electrons. Generally speaking, in redox reactions, metals react with metal ions. For example, aluminum metal reacts with zinc nitrate solution to produce aluminum nitrate solution and zinc metal. So aluminum, Al, is reacting, and zinc 2+ ions are also reacting. The nitrate is a spectator ion. It's not doing anything. The aluminum is converted into the ion form of aluminum, which has a +3 charge, and the ionic form of zinc is converted into the metallic form of zinc, Zn. We need to balance these half reactions. In the first half reaction, we can balance the charge by adding 3 electrons to the right side. And in the second half reaction, we balance the charge by adding 2 electrons to the left side. Notice that in the first half reaction, we're losing electrons. So this is called oxidation. In the second half reaction, we're gaining electrons, which is called reduction. When we add these half reactions together to find the overall balanced equation, we add them in such a way so that the electrons cancel out completely and don't appear in the overall equation. That means we need to multiply the first half reaction by 2 and the second half reaction by 3. That way, the 6 electrons disappear when we add the two half reactions together to get the overall equation. And there they are. Those are the 10 things you've got to know from Unit 4. Remember that this isn't everything in Unit 4, but these are the 10 biggest ideas from the unit. Remember that if you're looking for even more review and practice, the Ultimate Review Packet has everything you need to succeed in AP Chem. So go check it out over at ultimatereviewpacket.com. Hey, thanks for watching, thanks even more for subscribing, and I'll see you soon.